All right. Well, first, thanks, Vasco, for inviting me for this presentation. I remember I gave a similar one, a couple years ago. Yeah, and hello, everyone. My name is Zhong Liu. I'm a data scientist from NASA Earth Sciences Data in the Information Services Center, also known as NASA JESDISC. I'm also affiliated with George Mason University. Before the presentation, I would like to acknowledge my colleagues at JESDISC for developing and maintaining data services. So the title for today's presentation is Giovanni, the bridge between data and the science. So Giovanni is an example for integrating data from different satellite missions and the projects and conducting interdisciplinary research and applications. So if you don't want any coding, use Giovanni. Yeah, you can access over 2,000 variables. Yeah, and I'm going to give you some basic information on how to find and use data services at JESDISC. Over the years, we have developed many data services. It is difficult to present everything, in detail in 15 minutes. But I will focus on several key areas, including data search, online visualization, and analysis tools, such as Giovanni, a free online tool to explore and visualize frequently used data variables. So after this talk, you can use it for different purposes. So here's an outline of this presentation. First, an overview of the JESDISC. I will go through the history of JESDISC, key data holdings, and data services, because Giovanni doesn't cover all the data sets we archive, and it is helpful to know how to get the other data sets. So the JESDISC is located in Greenbelt, Maryland, in the Washington, D.C. area, and is one of the 12 NASA's Earth Science discipline-oriented data centers that manage, archive, and distribute Earth Science data. The map on the left is the distribution of the 12 NASA data centers. As you can see, they are located in different parts of the country. The photo on the right is the building of JESDISC on the campus of the NASA Goddard Space Flight Center. So JESDISC has a long history. It was established in the mid-1980s, the beginning of the satellite era. So for the interest of time, I will not go through the details. And let's go to the next one. Yeah. And these are some archive statistics about JESDISC. And these are multidisciplinary. There are multidisciplinary data holdings, including atmospheric composition, water energy cycles, and climate variabilities. JESDISC provides tools and services to facilitate data access and exploration activities. So more details about our data holdings, such as precipitation missions, near real-time products, and future satellite missions. You probably are wondering what these acronyms are. Some of you are more familiar with air temperature, rainfall, and so on. No worries. In Giovanni, we list the variables such as temperatures and the rainfalls. The top figure on the right shows the rainfall from Hurricane Katrina in August 2005. And the bottom one shows a polar vortex from MERA-2, a NASA global data simulation model. So these are some examples of data services provided by JESDISC, such as data subsetting, format conversion, regrading, customized data downloads, and value-added data services. The screenshot on the right is an example of satellite orbital or level 2 data subset. Also, how to find and access data services and the related information, such as documentation, FAQs. Here is the JustDisk portal. There are 3 sections in to this portal. The top one is for dataset and information search. The middle one is for assessing project and mission portals, featured images and news. The bottom one lists shortcuts and popular services and information. So let's go back to the top section again. The drop-down menu contains search topics such as data documentation and FAQs. The default is the data collection. You can expand browse data by categories below data collection and the search data set by different categories. For example, aerosols and air quality. So after you pick on the search button, click on the search button, you will get a list of related data sets and see the image on the right. And you can further refine the results by different categories, such as subject, measurement, temporal resolution, and processing level. So each data set link leads you to its landing page. This is very important because a data set landing page is a place for all data-related information and the services. This includes data summary, citation, documentation, and data access. There are 2 important things to remember from this talk. The first is the JustDisk portal, and the second, the dataset landing page. So JustDisk is migrating its data and the services to the cloud or Cumulus. This schematic diagram shows the framework, which allows data ingest, archive, distribution, and management. So for users, you will have the opportunity to analyze data at scale close to data in the cloud. In addition to this, user can access data from 12 discipline-oriented data center in one place for interdisciplinary activities. Now back to today's main topic, Giovanni. Giovanni is a popular tool developed by JustDisk in 2000. Giovanni stands for Geospatial Interactive Online Visualization and Analysis Infrastructure. Giovanni provides the means to perform 22 visualizations on over 2,000 variables in different earth science disciplines and from 6 different NASA data centers. So Giovanni includes many weather variables, such as temperature, wind, precipitation, from satellite observations and model data. The figure on the left shows the number of variables in different disciplines available in Giovanni. So with Giovanni assistance, researchers around the world have published more than 2,600 peer-reviewed papers in a wide range of earth science disciplines and other areas. For more information and an example about Giovanni, please visit the EOS magazine at eos.org on the right. The link information is on my last slide. So before Giovanni, we had to download data and develop data processing software. I took a remote sensing classes, with a floppy disk and an IBM PC in the 90s. So for variables that are not included in Giovanni, you probably still need to get the data and develop your own software if not available. However, more variables need to be added to Giovanni. Hopefully, all variables will be available in Giovanni in the future. So here is Giovanni's evolution. Back in the year 2000, with community software and the internet, we developed an online tool for data analysis and visualization. This was for the tropical rainfall measuring mission or TRIM data collection. Unlike today, it was difficult to use remote sensing data, as mentioned earlier. For example, many TRIM data were in HDF4 format, and not many users know this format well. Giovanni's current version can convert data in different formats and integrate data set from different measurements and disciplines. Giovanni's internal format is an SDF, a popular data format in the weather and climate community. The data download format is also an SDF. So the first thing to do with Giovanni is to find a variable for analysis and visualization. It is quite a challenge to find variables from over 2,000 variables. For example, if you search for precipitation, the result will contain 150 related variables. Giovanni has a different filters to narrow down the selection. On the left, you can filter the result based on observations, disciplines, measurements, spatial and temporal resolutions, and so on. On the right, you can also filter the result based on data source, temporal resolution, spatial resolution. So in this demo case, we select the recently updated Global Precipitation Climatology Project, or GPCP monthly precipitation. So the next step is to select an area of interest. You can choose a country, land, sea mask, US states, watersheds, and the world regions. In this case, we select Florida. We select time average the map for this case. As I mentioned earlier, there are 22 plot types for data analysis and visualization. They are grouped into 5 categories: maps, comparisons, time series, miscellaneous, and vertical. On this slide, some of them are grayed out because they don't support shape files like Florida for the time being. So we select the entire available time period from 1983 to 2020 for this case. Giovanni averages the data for this selected period. And here's the output window. It shows the time averaged map of the monthly GPCP over the past 38 years. As you can see, the precipitation distribution is not even in Florida. The Florida Panhandle has higher precipitation. The lowest precipitation is found in the Florida Keys. Options are available in the output window. You can adjust, for example, you can adjust the minimum maximum values of the map and the color palette. And you can change the map decorations and the overlays. And you can download the map in GeoTIFF, KMZ, and PNG. Oops. The data lineage provides data files in SCDF for each step of the workflow, which is very important for open science. You know, every step is very clear, you know, in Giovanni. So on this slide, it shows the input files used for generating the map we saw earlier. You can also download the result data from downloads in different formats, including SCDF, PNG, GeoTIFF, and KMZ, in addition to those in the lineage. So what Giovanni cannot do? Giovanni doesn't include the level 2 orbital data, for example, the image on the right. Doesn't include station data, airborne data, and other instruments like ground radars. Users cannot upload their data. Limited analysis and visualization. Performance can be an issue with high resolution data such as 0.1 degree IMerge precipitation data, and no user preferences available. So for future Giovanni's future include many upcoming requirements and capabilities. For example, the FAIR guiding principle, open science, we heard a lot today, and interdisciplinary research and application, data integration, and a lot of requirements. So it's very challenging to figure out, what the next Giovanni system will be. In addition to these, and also the accessibility from a third world country, like a smartphone, kind of applications. Yeah. So in summary, a large collection of Earth remote sensing and model data is available at the JustDisk. Tools and services are available for local and regional studies, as well as data exploration and education. Giovanni is an interactive online tool to analyze and visualize over 2,000 variables without downloading data and the software. We have 22 prototypes for visualization and analysis. So results can be shared with others, and data can be downloaded for further analysis and combined with other data sets. So future Giovanni is driven by user needs, science requirements, and technology development. That's my last slide. These are the information for today's talk. Thank you very much. I'm happy to answer any questions.
Thank you so much, Zhong. It was a really informative presentation. I'm a big fan of Giovanni, and I do encourage all the users and all the participants, to connect and try Giovanni if you didn't do it before. It really is a great tool. Zhong, I would encourage you to keep an eye on the Q&A. There's actually one question for you there. If you can answer on the Q&A, on the interest of time, we are running a little bit behind schedule, and we'll have time for a Q&A also later on in this session. Thank you so much.
No problem.
Next, we have Andrea Portier. It's a pleasure to have you here with us today. Andrea Portier works at NASA Goddard Space Flight Center in Maryland, USA, where she serves two roles: as the Global Precipitation Measurement Mission Applications Lead and as the Atmosphere Observing System Mission Applications Coordinator. In these roles, she leads engagement efforts with different stakeholder communities to understand and quantify how satellite precipitation data products are applied for decision-making, as well as creates capacity-building initiatives to promote and educate potential users about how NASA precipitation data can be used within their application activities to benefit their work and lives. Prior to working at NASA, Andrea served as a science assistant at a National Science Foundation in the Marine Geology and Geophysics program. Andrea holds a Master in Science and Geological Sciences from the University of Florida and received a BS and BA from Ohio State University in Geological Sciences and International Studies. Thank you so much for joining us today, Andrea. The floor is yours.
Thanks, Vasco, for the introduction, and thank you for the invitation. Can you hear me and see my screen in full presentation mode?
Yes.
Awesome. Again, many thanks for having me here today. So I'm going to be switching gears a little from the previous two talks and kind of focus on a specific mission today. And so my goal today is to showcase the use of satellite precipitation data, specifically a global data product from NASA's Global Precipitation Measurement Mission, or GPM, for applications. I do hope this starts a dialogue with you all to show how this product can be used across different spatial scales to support a range of applications and to possibly use this data within your systems or models or apps that you're developing. Before I get to that data product, I do think it's important to give you a very brief, and I mean brief, overview of the GPM mission. So what you see on the screen here is a little bit insight about the GPM mission. It was launched in 2014. It's a joint mission between NASA and JAXA. The GPM mission actually builds off the tropical rainfall measurement mission that measured precipitation over the tropics. What's unique to GPM, it expands that coverage to measuring precipitation from 65 degrees north to 65 degrees south, really capturing global precipitation where most of the majority of precipitation falls, as well as majority of the population lives. What's unique to GPM is it has two concepts. One is it carries two advanced instrumentations on board the GPM core satellite, but also GPM works with a range or a constellation of other satellites from national and international agencies. To give you a brief glimpse into those two advanced instrumentations and their capabilities, I'll first start with the GPM microwave imager. Essentially, it's a passive remote sensing tool, and it helps provide surface precipitation estimates, really understanding the intensity and distribution of precipitation. What we like to do is have an analogy of kind of similar to what an X-ray scan of precipitation would be on the surface. The other instrument is the dual frequency precipitation radar. This is an active remote sensing tool, and it provides 3D observations, precipitation structure, precipitation particle size, as well as precipitation intensity and distribution. What's really cool about this instrument is that it can allow us to see inside a storm and see the development of a storm going on. A great analogy for this is a CAT scan. While we have these two instruments and advanced instruments, they provide swath data. So they provide really limited coverage. And so you may be wondering, how do we get to that global precipitation? And that's where the constellation's coming in. The goal of working with a constellation of satellites from other national and international agencies is to have them feed precipitation data that they're collecting from their satellites to that GPM core satellite, where it serves as a calibration tool to provide global precipitation measurements through the global data product called Integrated Multi-Satellite Retrievals, or GPM, or for short, iMERGE. The concept of iMERGE is that, again, it combines all passive microwave precipitation information from these satellites into a regular grid and interval with using interpolation methods to obtain a complete coverage. And so I know I'm going through this quickly, but I really want to get to those use case examples. So what does this global data product have? And I think this is a great example of it. This is a view from September in 2018. We had 4 storms that were developing across the Atlantic. You see a major typhoon in the Pacific, as well as several mid-latitude convective systems, as well as even frozen precipitation near the poles. And this is really what that iMERGE product brings you, a global picture of where, when, and how much rain and snow is falling across the globe. So to give you a little bit of the characteristics of iMERGE, actually, if you were here on this workshop and participating yesterday, Vasco alluded to some of these characteristics yesterday. So iMERGE provides surface precipitation estimates near globally at about 10-kilometer resolution and down to every half hour. And we have a data set from 2000 to present. And you may be wondering, why 2000 when the mission launched in 2014? Well, it's in a very high level way. The iMERGE algorithm team combined data from the TRIM era into the GPM era to make one consistent global precipitation data set from 2000 to present. iMERGE has 3 different latencies, so different products. And latencies means the time this data is available after observations. So the iMERGE early run product is available 4 hours after observations. Essentially, it's quick precipitation estimates. It doesn't have any gauge adjustments, and there's no backward propagation. So this is quick data that can be used. And then we have the iMERGE late product that has a latency about 12 hours, so it's available at that time frame. Again, it has no gauge adjustment, but it has more input from the constellation, so it's slightly more accurate than the early run. And then you have the iMERGE final product that comes in about 3 to 3.5 months after observations, with the full algorithm development, with a complete input of constellation estimates and monthly gauge adjustments. So it's what you could call probably the most accurate out of all 3 products. However, the latency is longer. What's critical about having these different latencies is that they can enable a range of applications. The early and late run, because of their almost near real-time aspects, is that they can enable a range of applications to support operational uses in real-time processes. The final run, while it's slightly more accurate, again, this might be better to support research applications in terms of evaluating trends, looking at climatology that can support other applications that you might be interested in. Just a quick heads up that the available versions of final is already at version 7, while late and early are still at version 6. So please look at the documentation for more information about that. Okay, so what I want to do for, I think, the next 8 minutes with my time that I have, I want to explore the use of iMERGE for enabling applications. iMERGE has enabled hundreds of applications around more or less 6 thematic application areas, from ecological management by using iMERGE to monitor changes in precipitation associated with animal migration patterns, to even water resources and agriculture, looking at the assessment of freshwater inputs and basins, to quantify water fluxes, to even the inclusion of precipitation from iMERGE in crop forecast modeling. For energy applications, We have, again, the use of assessment of freshwater inputs using iMerge, but for hydropower generation and development of the infrastructure itself. Shifting towards disasters, that's where a lot of our organizations are that use iMerge for disaster mitigation, monitoring, and response, where we have the use of iMerge for landslide nowcasting, incorporation of iMerge in hydrological models for flood estimation, for disaster insurance or index-based insurance for defining thresholds for insurance payouts, to even situational awareness of extreme precipitation in potentially affected areas. For public health, we have organizations using iMerge to track precipitation anomalies and predict vector and waterborne diseases. And last but not least, within the weather and climate field, we have the use of iMerge for real-time to improve precipitation forecasts, as well as the long-term data set to validate climate models. And again, I just want to throw some quick examples to get this dialogue going. But right now, what I want to do is to give you some of the organizations that are actually using our data. And this is going to be kind of high level. I welcome people to reach out to me to talk even more about these concepts and examples. So the first one I want to highlight is European Union's Emergent Response Coordination Center. What they do is collect and analyze real-time information about disasters. They monitor hazards and prepare plans. One of their key actions is to develop daily maps to provide an overview of a situation that's happening. And so where iMerge comes in is that they use 7-day accumulation estimates from precipitation estimates from iMerge, along with socioeconomic data to tell where humanitarian assistance is needed most. I have two examples from, I think it's 2019 from the flooding in Iran, where they're showing where precipitation hit the most along with socioeconomic data. Along with in Guatemala, they're reflecting back on this rainy season to see where areas that are most at risk for, let's say, landslides, transportation hazards, as well as food insecurity, and for the risk where assistance may be needed throughout the coming days. To get to still on kind of the disaster side, kind of switching gears on top from situational awareness to how people actually use iMerge within hydrological models. This example is the use of iMerge real-time. So I believe it's late that they're using in this situation into the global flood monitoring system. This flood monitoring system is a system that is developed out of the University of Maryland. You're welcome to go to that site. It's a fantastic and really cool tool, so I encourage everyone to check out. But it's this system is a real-time quasi-global hydrological model that ingests iMerge into the system to see if precipitation extremes fall above those thresholds where flood susceptibility is high. And then you're able to use their tool to see those areas of extreme precipitation to see if areas that might be prone to flooding. So what I have here is a quick example of Hurricane Ida. Hurricane Ida made landfall in late August in southern United States and made its way all the way up to northeastern United States. And so on the left is just it's a visual that I screenshot of just showing how much wind, where, and how much rain is falling using iMerge. And then showing me zooming in on this product, I think it has a higher resolution than iMerge of looking at the flood susceptibility in areas in southern United States on the top frame to the right, and then flood susceptibility in the northeastern United States after hurricane had passed. I encourage people to look into it. Again, I just want to go over briefly this with respect to time, but I'm happy to talk about this more and the concept of this model later. Switching gears to public health, as I quickly mentioned that people are tracking precipitation anomalies to predict vector and waterborne diseases. A great example is researchers at that time from University of Maryland, now University of Florida and University of Maryland. They're directly engaging with public health officials throughout countries such as Yemen, Haiti, South Africa, and Bangladesh to predict areas that are most prone to cholera and send out public health alerts. How they do this is that they combine iMerge near real-time data with other environmental parameters such as MERA2, looking at temperature data, as well as socioeconomic data from the World Health Organization, UNICEF, and NASA CDAC, so the socioeconomic platform there. And how they do this is that areas that are prolonged warm temperatures, areas of higher than heavy rainfall than usual, along with water insecure areas, are more at high risk for cholera. And so what they did was they show the prediction in West Yemen. They show that there's potential risk of cholera outbreak in those areas. And once public health officials went through and had tracking of cholera-prone cases, they saw a very high correlation to the prediction and observations. So they began to realize that this is a good tool to use and also send out public health alerts. Switching to water resources and agriculture, we have a researcher out of the University of Washington that's working directly with farmers in northern India and Pakistan to use integrate iMerge real-time data with smart agriculture equipment, along with GIS data and farmer information into a system called PANI. It's the provision of advisory for necessary irrigation. The concept is that the farmers directly get irrigation alerts of when and when not to water their crops directly through cell phones. So a very simple text that works for the farmers. And what I find interesting about this is that they definitely use a data-driven approach where they work directly with the farmers to cater to their needs to make a successful application of the use of environmental parameters to work and help conserve freshwater resources. On the lines of water and agriculture, I think my time's almost up here, but I do want to highlight the use of iMerge as another validation precipitation data set. So the USDA Foreign Agriculture Service generally uses CHIRPS, another precipitation data set. iMerge comes into handy as it's almost a near global precip data set that it stretches outside the 50-degree north latitude that CHIRPS has. So it can help with crop production estimates and assessments outside those latitudes, but also it comes in handy for real-time information when other precipitation data is lacking at that time. And that's what the example is here, is that CHIRPS wasn't able to provide information in the north central region of India. However, real-time data of iMerge using iMerge was proved useful to provide crop assessments in that region. Okay, with time, I'm actually, I'm going to just do this example and then move over. This quick example of the index-based insurance. And all I want to do is highlight where we have people that are using the longer time record of iMerge from 2000 to present developed thresholds, as well as real-time data to see when precipitation falls above or below those thresholds to communicate and communicate to clients when to receive payouts based on a disaster event for index insurance. So this has been a very important part for insurance sector on the use of real-time precipitation data, especially from satellite coverage. Real quickly, just to wrap up in this last minute, is that I know there were some questions yesterday of how do we know when to trust iMerge? The algorithm team came up with a simple quality index to give some guidance on the degree to trust iMerge. There's two types of quality index, half hourly and monthly. I'm going to just say, please go see the ATB document via the GPM data directory, because it has how to use this, how this can be useful to your work. I will note that the big thing is that while we have this guidance, it's based on the user to see if this is appropriate for your application. So it's based on just a red, yellow, and green flagging system. So essentially, if it's red, it might not be the most, it's a higher uncertainty of data for iMerge versus green. It has good skill scores for the iMerge data set. Real quick, just to say that if you go to the GPM data portal, it's a great way to start of exploring what data products we have, where you can download the information, and even has links to what Zhong talked about for the Giovanni. It's a great source and visualization tool that you can use. And so I'd recommend going here to start out and see the capabilities, what we have, or please reach out to me. So I will stop there. I know I flew by, but I hope this just starts giving you an idea of how you could use iMerge for a range of applications, not just at the global scale, but this local and regional scales and the capabilities of iMerge. So please feel free to reach out to me if you have any questions or comments. I'm here and I'm happy to answer any questions as needed. Thank you.
Thank you so much, Andrea. It was a great presentation, a great overview of a really important set of products, including iMerge. A lot of people are using them, so it's always good to hear about them. Andrea, please keep an eye on the Q&A box. We have questions coming in. And again, thank you so much. Also, we apologize on the delay. We have had a few technical issues earlier. We're trying to get back on track as much as possible. And our next speaker is Jürgen Decloedt from VITO. He's an international business developer within VITO remote sensing in Belgium. And his main goal is to build a bridge between research and industry. Developing value for both VITO and the customers is what gives them energy. After retrieving or getting a master's degree in criminological sciences, Jürgen worked for Philips, Teleatlas, and TomTom in various commercial roles. From 2014 till 2016, he led the territorial affairs business unit of an SME specialized in building software for local governments. 2016, he joined VITO remote sensing team. Jürgen is passionate about customer experience and a true believer on the enormous potential of remote sensing for the industry. Thank you so much for joining us today, and the floor is yours.
Thank you, Vasco. Thank you for having me here. Let me share my screen. All right. Can you see my screen?
Yes.
All right, brilliant. So the presentation that I bring today is really focused on a downstream application example that we developed within VITO, specifically for the potato industry, so the potato sector. So I'll try to bring a condensed story on how we use various sources of remote sensing data to bring value to the potato processing industry and the potato farmers. So, short introduction to VITO. VITO is a research institute in Belgium where we focus on technology on the crossroad of sustainability, and we're on the applied side of things. I myself work within the remote sensing unit of VITO and have a focus on everything that has to do with agriculture. So some background on why we started this program on potatoes. Potatoes is one of the most important staple food products in the EU, and Belgium is one of the biggest frozen potato exporters of Europe. So there's a huge interest in and a very big industry in Belgium and in Europe on potato processing, and there is a need to grow more potatoes, but also some challenges. So not the least the climate change that is hitting also the potato industry, of course, and already quite some years ago, the vision of the industry was that they should digitize their way of working and that they have a need for new instruments, tooling, and insights. So we developed this first in a R&D project within the iPod project, the Industrial Potato Monitoring Project, which we rebranded afterwards to the What You Grow application. There was a company in the US that already claimed the iPod brand name, so we could not use that. So we changed to What You Grow. So once the research was done, we have continued the insights and the learnings that we retrieved there within an application that we still host to date and make available to the broader sector. So what we developed is a satellite-based data platform where we monitor all arable crops satellite-based, mainly by making use of the Sentinel data, but as it is a data platform, we also integrate quite a bit of other data sources there, and they're used to either calibrate, validate, or develop new satellite-derived products. And the goal is to help the potato sector in increasing their yields, or the arable sector increasing their yields in a sustainable way. Now, as the focus was on potatoes in the initial project, I kept the focus also in the scope of this presentation on potatoes. What we did is we started off with Sentinel-2 data and Deimos data that we started making available and processing, and we derived some information out of this data. And later on, we also introduced Sentinel-1 data and developed a fusion product that allowed us to create an uninterrupted time series of NDVI, in this case, VAPAR values at parcel level. So what you see here is on screen is we found a correlation where we, in clouded periods, rely on the SAR data of Sentinel-1 to derive or predict the values, the VAPAR values that would otherwise have come from the Sentinel-2 sensor. And whenever we have a Sentinel-2 optical observation, we use that, and also to correct for any deviations, if any, from the past. In this way, we can create a very smooth and uninterrupted phenology curve of any parcel, basically anywhere in the world. So we started developing a number of products where we followed up on the crop growth, so on the phenology at parcel and interparcel level, and used on the one hand ground truthing sampling data for that, and used quite a bit of drone data and hemispherical images to calibrate and to validate the indices that we derived from the Sentinel-2 and the Deimos data. So the validation focused mainly on F-cover and VAPAR, but also on later on LAI, so on leaf area index, and the algorithms that we used were provided by INRAE through the BVNet algorithm. So throughout the project, we started mapping the various phenomena of the phenology during the phenology, so being starting from sprouting, germination up to senescence of the crops, and map that on this various phenology on the phenology curve that we derived from satellite imagery, and again used the FAPAR values for that. So on top of that, we developed a yield forecasting model where we used a combination of various yield models for 3 specific potato varieties, which are predominantly available in Belgium, the Netherlands, France, and Germany, and created such a yield forecast on field level, and then also, of course, aggregated to higher administrative levels. And to develop this model, or this yield forecasting model, we used both climate data, soil data, an actual database of actual yields, and then the indices that we calculate, of course, from the satellite data, from the Sentinel-2 and Sentinel-1 data, along with a set of field observations. And this has been put in the model, which runs now autonomously, and where we to date still predict yields at parcel level for these 3 varieties. So, of course, training was a very big part of the job, and there we collaborated intensively with both the processing industry and an agronomical research institute in Belgium, which provided all this training data to us that we could use in the yield models. So to give you an idea on without going in too much detail, but we used a combination of two yield models, Aquacrop and Wofost, where to date it's still a fusion of these two models that we use, and that's still in combination, of course, with all the other data sources previously mentioned, so soil data, meteo data, and ground truthing data, but in a very, very fragmented way for that last data point. So maybe to summarize, so we use the platform, the What You Grow platform today as a demonstrator platform for everything that is possible in the agricultural and the arable domain from a remote sensing point of view. It has been adopted in the meantime by other actors in the value chain. Amongst others, we have agro-insurance companies that make use of the data in the framework of a broad weather insurance, where damage or claim handling is handled through the application, and where the satellite-derived data is used to assess eligibility of claims and scope of the claim. It is used by input suppliers, seed breeding companies, or crop protection companies to assess the effectiveness of their and performance of their products, both in a trial condition as in real world conditions, so at farmer fields, if you like. There are integrations with machine builders that provide, again, data coming from the machines, which on their turn can be used to train new models and improve and develop new products. Of course, food processors are still on board. Farmers, which of course are the key users and contributors of the platform, and we share the platform with other R&D institutes to have an innovation flywheel in the agricultural/remote sensing domain. So it's really used to showcase the potential of EO data for agriculture in Belgium, and also serves as a data platform that can be used to derive new insights in either the EO domain or any of the other mentioned domains. So that was in a nutshell. I think I made up some time for you, Vasco, in this.
You did. Thank you so much.
This way. So happy to answer any questions or go in more detail on all the parts if that would be required.
Yeah, I do have a question. So what other crops are you planning or already monitoring? Is there some integration, or for instance, a farmer who's growing different types of crops can use like the same application, or will we have to use different applications? What's the current status?
Yeah, so good question. So the status today is that we monitor all arable crops and vegetables, which take a minor part of total arable lands, and have managed to also integrate various players in the value chain, like for example, a breeding company in sugar beets, a company that develops harvesters specifically for maize, for example, biochemical companies that focus on wheat. So in fact, it covers all arable crops, and we try to connect as much as possible with all stakeholders in the value chain. And maybe I haven't mentioned that part, but we've set it up as an open platform. So there is communication in API based in two directions possible for anyone who partners up in the bigger project that we have set up.
Thank you so much. I'd like to ask you to keep an eye on the Q&A box. And I also see on the chat box, there's also a question. And if you can answer directly to our participants, I would appreciate that. Thank you again for your presentation. It was extremely informative.
Thank you.
Next in our program, we have a presentation by Dr. Claude Duguay, who is a professor in the Department of Geography and Environmental Management at the University of Waterloo, Canada, and a visiting professor in the Department of Earth Sciences at the University of Coimbra. He's also the founder and scientific advisor of university research spin-off companies H2O Geomatics and Hydro-EO. He has published extensively on the topics of remote sensing of the cryosphere and surface water, climate change, radiative transfer, and lake modeling. He has been an investigator of several projects of the European Space Agency and the Canadian Space Agency, and is currently involved in the development of the terrestrial snow mass mission concept of the CSA, the Copernicus Imaging Microwave Radiometer Level 2 product, and algorithm development, as a member of the expert user group, and the development of the lake ice cover and lake ice thickness products in ESA's CCI Lakes project. Thank you so much for joining us today. Claude, the floor is yours.
Okay, thank you. So you hear me well? Do you see my slides?
It is in the presenter mode, not the... Yeah, so I can see the notes. Okay, perfect.
Perfect there?
Now I can see the entire software. So the menu bar.
Okay, but now I put it...
Can you swap displays? Top left, please.
Swap displays, yes.
Okay, perfect.
Perfect.
Thank you.
Okay, so thank you for the invitation. I'm going to talk today about actually the ESA Lakes CCI project that I've been involved in through H2O Geomatics. And what we've done in this project, it's been running for over 2 phases now. The first phase 1 ran from 2019, 2022, and starting 2023 until 25, we are continuing to improve algorithms for studying the impact of climate change on lakes. So it is the first time actually that there's a multivariate data set of site observations for lakes that is produced for studying the impact of climate change. In the past, we tended to study, for example, lake ice from satellite imagery, for limited time record, and other variables, such as lake surface temperature and so on. But here, what the attempt is to work on some algorithm to develop the best product as possible, and then merge them into a common grid. So I will be talking to you first of all now why lakes, how do we derive these products, and then where you can find some of the data that we've been producing. So why study lakes? Of course, there are many lake hydrotrophic biospheres that are indicators of current climate change. They're distributed globally. Of course, some regions, such as Canada, where I live most of my time, is covered by a very large number of lakes and reservoirs. They are subject to both natural and anthropogenic pressures. They respond quickly to changes, and they also affect the quantities of greenhouse gases to the atmosphere. And they also affect local and regional climate and weather. And taking as an example from North America, we know quite well documented what we call lake effect snowfall that is generated in the Great Lakes regions of North America. They store signs of also change in their sediments. And there's been some, of course, interesting studies conducted through reconstructing past climates using sediment cores. So the questions here in this project is, what are the linkages between lakes and climate? And are these linkages measurable from Earth observation satellites? So there's, of course, an increasing body of evidence on the response of lakes to climate change. Some of that in the past, and these are various pieces from titles of various articles that have been published over time, based on in situ observations, and some of those also from remote sensing observations. And we also have studies that have focused on the use of lake models to look at the impact of climate change under contemporary climate conditions, but also making also some projections of possible changes in lakes into the future. So regarding EO observation, especially in the context of ESA, there's been an increase in, of course, the use of satellite observations to document changes in response to climate. And what we're seeing here on this slide is the number of satellite missions from the European Space Agency that have been used to monitor climate change. And on the top right, the graph what shows us the number of papers over time that have used some of the data from the European Space Agency alone. No, so the project that I'm involved in is called the Lakes CCI project from the European Space Agency, and basically what the European Space Agency does through the CCI project, which is Climate Change Initiative, is to take some of the recommendation from the Global Climate Observing System to observe what they call essential climate variables. Some, of course, documentation of changes in climate, climate variables are either from in situ observations or satellite observations. But being an ESA project, of course, the emphasis is on space-based observations. But we do use, in some cases, some of the variable in situ measurements for the validation of the products we develop. So for this project, we are deriving 6 variables, what they're called thematic variables. So the ECV is lakes. If we look at the GCOS documentation, the most recent documents that the reference here on the right, the most recent version, 2022 version of GCOS, we have lakes is the variable, and then under that lakes variable, there are thematic variables. And one of them is lake water level, then there's lake water extent, lake surface water temperature, lake water leaving reflectance, lake ice cover, and lake ice thickness. And so what the project aims to do is to, based on the GCOS requirements, it tries to fulfill some of these requirements in terms of accuracy, in terms of stability of the measurements over time, because we're building time series. And of course, we need to document the uncertainty of each of the variables that we provide. So if we look at, to provide you with kind of an overview of how these, first overview before moving to the details for each of the variables, how each of those variables, so for example, we have on bottom left, we have LWL, which is the lake water level, is derived from the radar altimetry measurements. Then we do have also, below that is LIT, which is the lake ice thickness, is also derived from radar altimetry. To the right, then we have the lake water extent, uses a combination of estimates from altimetry for the water level, and as well as some optical data. And then for the lake ice cover, it's a combination and mostly focuses on the use of optical data, but also supported by some thermal remote sensing data. We have lake water leaving reflectance, which is optical data, and then the lake lake water surface temperature is derived from thermal remote sensing. And this is pretty well expressed in the importance of all these variables within the diagram on the right, where we look at the impact of climate change and affects the surface energy balance, the water balance, wind mixing, and so on. And some of these variables that we're deriving, lake ice cover and ice thickness, lake surface water temperature, the lake mixing regime, and lake area and water levels are all variables, some of the variables that we're deriving in this project. So let's take a look at the very briefly, 6 slides that show one slide per, actually 5 slides that will cover the thematic variables. So the first thing is water level. This is derived from radial altimetry, looking at data back from 1992 over a sample of lakes around the globe. And this is, we use a KU band frequency to derive this. So it's using data from European Space Agency satellite and the French and NASA satellite combined missions to derive this. Then from the water levels, what is derived is there's a relation between lake water level and water extent. And this is a relation with dipsometry. So basically, we look at the extent of the lakes in relation to the water level. So at the bottom, what we have here in this graph, which is quite difficult to read, we have on the x-axis the lake water level, and on the y-axis we have the lake water extent. So it's looking at some lake, it's the relationship between the two, dipsometry curve that is used to monitor the lakes. For lake surface water temperature, it's derived from, of course, the main measurements are in the thermal part of the electromagnetic spectrum. It is using moderate resolution, roughly 1 kilometer resolution. There is some use of visible and infrared data to detect the open water, but and because of that, of course, the measurements are at this point in time, the measurements are only provided for daytime observations, not the nighttime. It uses a more complex retrieval than in the case of the lake water level, which is more straightforward. In this case, there's a forward modeling done of brightness temperature using a rate transfer model. There's some weather predictions, first guess that go into this. And after that, of course, there's the measurements of brightness temperature measurements from the satellite missions, the various satellite missions over time. And some of the outputs are the most probable water temperature. So there's some flags in terms of reliability of the measurements for each pixel, and some quality estimate. So what you see on the right, this is a precursor to the Lake CCI product. The algorithm has evolved over time, but provides you with a general idea of how this type of data can be used to look at changes, trends over time in lake surface water temperature. Another product is the lake water leaving reflectance. So as the term says, it's the leaving reflectance from water. And from this, what is derived is the chlorophyll A, and turbidity of the lake, some of these measurements. And of course, as all the other variables, uncertainty measurements are provided for the different versions of the product we've been developing. On the top right, what you see, this is the polymer algorithm, which is used on the data that shows a relation on the y-axis, the remote sensing estimates versus the in situ measurement on the x-axis for different lakes. These are different lakes around the world used. And at the bottom, it's an evaluation of the performance of the algorithm for chlorophyll retrieval, a combination of different lakes in this scatter plot. Between, of course, in situ measurements on the x-axis and the retrieval on the y-axis. The lake ice cover, this is actually my group is responsible for deriving the lake ice cover product. And we do, I will mention that a bit more details in a couple of slides from now, but we monitor right now over 2,000 lakes globally. But of course, there's some lakes around the world that do not form an ice cover. So what we first do is a priori determination of whether a lake may form ice or not. And for that, we use our lake ice model that we've developed. And then after this step, then once we identify the lakes that potentially form ice cover, we use MODIS. And so in our case, so far, we've not used the data from European Space Agency. We use the NASA data, MODIS, the full archive from 2000, and now up to processing 2022, which is, I think, over 1.3 petabytes of data that we've processed. And we process the data through random forest algorithms for machine learning of manually labeled images. And what you see on this example on the left, we have derived ice cover, open water, and cloud cover for 2 dates during a low ice season in the Great Lakes region of North America. And on the right, the high ice season in 2014. For lake ice thickness is a new product that is being introduced in Lake CCI. It's relatively new. So at this point in time, it's been derived, and there's a product, a time series being produced since 2002 for a single lake, Great Slave Lake in northern Canada. And the principle here of radar altimetry for retrieval of lake ice thickness is that we get a signal, the KU band signal at nadir goes, if it's dry snow, it goes through the snow. There's a reflection of signal on the waveform at the ice snow interface, and then a second reflection at the ice water interface. So what you see on the graph, the waveform, is these returns from the two reflections at the two interfaces, and we use that actually to retrieve the ice thickness. And so what you see on the right then is in the middle, these are retrieval from the JSON-2, JSON-3 satellite for some overlapping time period in 2016. And overlaid on that, we got some estimates from the thermodynamic lake ice model, as well as in situ data. So there's a pretty good match between the measurements and in situ measurements, the lake ice model, and the retrievals from JSON-2, JSON-3 within an accuracy of about 10 centimeters. Now, about the product itself. So I've talked about how we derive, very briefly, each of these thematic variables. So there is a spatial temporal coverage here providing this map. It's 2024 lakes. It's not all the thematic variables that cover 2024 lakes. In the case of lake surface water temperature, it's that number, but in the case of lake water level, it's a smaller number, and so on. We try to cover as long as possible time series from different satellite missions. So some of them started in 1992, some started a bit later in 2000, as the case for lake ice cover. So right now we have delivered, it's available to users. We have version 2.02. We are about to release in the fourth quarter, at the end in December, version 2.1. And then there will be a release in 2025 of version 3.0 when there'll be further improvements to the algorithms, further validation that will take place. In terms of data overview availability, here on the left, you have an idea of the timescale, but also the data aggregation. So it's on a common grid. Some of the data, for example, the MODIS, we use 250 and 500 meter resolutions, but we aggregate that into the common grid. And one of the main reasons is the lake surface water temperature is on a 1 kilometer grid to start with. So we brought everything in on that same grid. The data is available on CEDA, and that you have the link here. We also have a WebGIS that's been built. There's also some Jupyter Notebook examples are available, and also a dashboard has been produced for the project. So before my last slide is I'll provide you with an idea of the content of the WebGIS. It's for data visualization purposes. It covers all the variables, but the reflectance is not provided, but the chlorophyll A turbidity are there. You have the link provided here. You can actually generate time series plots, animations, and then you can also share it in any instance of your session with other users. And these, what you see here are different examples from the maps, the different variables, and then plots that can be generated from through the WebGIS. There's also a dashboard, and so that allows visualization of changes in the lakes. So there's through aggregation methods by country, by continent, altitude, population pressure, and so on. So far, we're in the early stages of this the dashboard, and for the time being, lake surface water temperature and lake ice cover are the two variables that have been integrated into the dashboard. You see two examples here on the bottom left. There is a Great Bear Lake in northern Canada, and what we see here is at the continental North American scale. So you have the orange. If you look at the time series, we have a variability in lake ice cover over all of North America, and then we have at the top the dashed white line is for Great Bear Lake. So there's different ways of visualizing the data. And on the top right, we also see lake surface water temperatures that are provided. So we have you see the maps, the graphs, and then one can compare different lakes around different regions of the globe. And with that, well, thank you very much for your attention, and I'll take any questions.
Thank you so much, Claude. It's really interesting work and massive work monitoring all the lakes, or so many lakes around the world. I do see 3 questions in the Q&A box. I'd like to ask you to please answer those questions there. And in the meantime, if the participants have other questions, please type them into the Q&A box as well. And Claude, if you don't mind answering them there, I would appreciate it. Thank you so much. We're moving on to our last speaker of this session, Alex Chunet from ESA. Our last speaker is the European Space Agency representative to the World Bank, hosted at GFDRR, and supports the coordination of collaborative activities under the ESA partnership and the Joint Space for International Development Assistance initiative across the World Bank. He previously worked for the World Bank from 2017 to 2020 as a geospatial data scientist, and contributed to the deployment of Earth observation technologies and their application and adoption within World Bank operations and analytical pieces. Subsequently, he also led the development of the first geospatial strategy of the Agence Française de Développement, and he holds a Master of Science from the London School of Economics, a Master's in Public Management from Sciences Po Paris, and has completed trainings from the MIT, the French Space Agency, EUMETSAT, in data science and Earth observation technologies. Alex, thank you so much. I apologize for the delay, and the floor is yours.
Thanks a lot, Vasco. Can you confirm that you hear me fine?
Yes, and I can see the slides.
Perfect. So thanks a lot for the introduction, and great to see the presentations of the other panelists today. Very impressive work. So my presentation is going to be focused on the more, I would say, institutional question, which is about the mainstreaming of Earth observation in international development projects. And when I say international development projects, I mean how we can better liaise with international organizations and development banks in order to not only mainstream those technologies within their operations, but use them as channels and kind of tunnels to reach developing countries and increase the use and integration of those technologies in those countries. So that's going to be the focus of this last presentation. So as we saw in the previous presentations, and I'm sure also yesterday, there is thousands of use and applications of frontier Earth observation, and also now with AI, there is the possibility to use those technologies on many different sectors: agriculture, environment, disasters, climate change, urbanization. So many applications available out there. Those technologies allow to monitor many different indicators, variables that allow to have better information on our planet, and therefore to better plan, monitor, or evaluate the interventions that we're pushing forward. And also, there is a new kind of paradigm, which is the space for development paradigm, in the sense that there is an increasing overlap between those capabilities and, let's say, our strategy and our priorities in terms of sustainable development in international development. And this reflects also in developing countries through a growing I would say, interest and need related to those technologies. It's not very well known, but there's actually 21 African countries that have a space agency or a space program, which means that there is strong demand for more accessible and frequent data. And those programs and agencies are often focused on tackling environmental challenges and building skills. So it's a new dimension that we have to take into account. And the idea is, how do we tackle this need, right? How do we ensure that all those applications that we have can be mainstreamed and can be adopted across the world in those different countries, in Africa, but of course, in every other continent. So this is exactly what at the European Space Agency we've been working on, right? And there is different dimensions to it. First, there is the dimensions of availability and accessibility of the data. One of the programs, and I do not mean, of course, that it's the only program at all, because there is beautiful work being done by the private sector, by NASA, by JAXA, but one of the programs is the Copernicus program, right? And this one really fulfills this role of increasing availability and accessibility of data. However, we need to tackle other dimensions if we want people to use this data. It's not by making data, Earth observation data more specifically, only available and accessible, that we can expect that it will start being used by every other actor that could take value from there, right? Because the reality is that the gap between accessibility and adoption is huge, and we need to support actors, support public and private entities in adopting and integrating those data. And this is the reason that at ESA, we've worked on different programs called EO World, EO4SD, and GDA, which tackle those different dimensions, going from availability and accessibility to awareness, acceptance, and adoption, in order to increase exactly the use and the mainstreaming of those technologies. And again, here, those three programs I mentioned are specific programs that target international organizations, and in particular development banks, right? Because that's kind of what the focus I wanted to put on this intervention today. However, there is, of course, other programs from ESA that are very relevant to the mainstreaming globally and the adoption of those technologies. These three programs that I was mentioning are basically a sequence of programs that we have been unfolding since 2008. So since 2008, we've started with the EO World program, which was really about raising awareness. Then we had the EO4SD program, which were more about consolidating requirements. And now we have the GDA program, which is really more about the mainstreaming and transferring Earth observation into operational working processes and financing within international financial institutions. And I will give a few examples just after to make this more concrete. But the idea is that we have those different programmatic vehicles through which we've been supporting those institutions in the integration and mainstreaming. And those are ESA funded programs, right? So to take the example of the partnership between the European Space Agency and the World Bank, we've basically been working with the World Bank since 2008 with the objective of fostering the integration of Earth observation technologies. And this right now basically is taking the shape of the partnership through which we're supporting 61 World Bank projects. And this is based, of course, on the GDA program, which has itself a budget of around 38 million euros. The way we're supporting those 61 World Bank projects is actually through the European ecosystem. We work directly with private companies, institutes, and academia from the European continent and recruit them to answer to the needs and requirements expressed by development projects around the world by the World Bank in this specific case, but also with other development banks. And this has resulted in this specific graph, if I had to summarize it, which is basically the share of projects at World Bank that mention in project documentation the use of Earth observation. And we see that there's been a steep increase between 2010 to now, from 2% to around 12-13%. So this is really what we've been supporting and aiming at, right? It's the increased use of Earth observation data and technologies throughout the portfolio of projects in every sector at the World Bank. Something to clarify, of course, is that we do not pretend that this trend is only the cause or I mean the consequence of the ESA World Bank partnership. There is, of course, other trends. There is other contributing agencies, JAXA, as I was mentioning. But let's say that we've been happy to contribute to this trend to a certain extent. So Just before I show a few examples, what I want to clarify also is that the GDA program, as I was mentioning, is based on the European ecosystem. And here you can see the list of the 14 participating countries on the European side. What that means is that in those countries, we work directly with industries, institutes, and academia, and we recruit those entities through basically by consortium. We recruit consortia of those entities through public tenders that are published by the European Space Agency through its ESA Star platform, and those tenders are labeled GDA. So just mentioning this in case some of the people today would be interested in those potential tenders through which we recruit consortia of companies to support development projects around the world. So what is important about the GDA program is that we target many different sectors, right? It goes from disaster resilience, climate resilience, fragility, urban sustainability. So all sectors that are linked to sustainable development. And right now we are supporting, actually, if we take into account World Bank, but also the other development bank, more than 80 projects in more than 50 countries. And what's important about the support that we provide is that we have tried to move away as much as possible from just an ad hoc way of working and let's say a unilateral or one direction supports. It's really the partnerships that we build with development banks around the world are really two-way partnerships through which ESA covers the technological part. So we mobilize those consortium of companies and entities to implement a product, a service, a tool on different topics related to the use of Earth observation. And then the blue wheel, basically the international financial institution, comes in with funding to cover the capacity building activities, the skills transfer activities that will allow to transfer those tools and those services, this data, and ensure the adoption of those tools and those technologies by the beneficiary countries. So it's really a complementary approach where ESA covers the technological part and the development bank, international financial institution, covers the organizational change part, where they ensure that once we have designed the tool, this is taken forward and that we're training people on the ground to use it, right? So that's really the perspective here. We've also gotten in the ESA program itself some inspiration from international development practices, right? Because we have actually a component that is called an M&E component, which is something that is more often used actually in international development. But there's really this idea of cross-feeding between the two sides, and I could come back on this later. So in order to implement actually this coordinated strategy, specific programmatic structures have been created on the side of the different development banks we support, and specifically on the side of the World Bank and the Asian Development Bank. At the World Bank, there is a new team that has been set up in 2021, which is the Digital Earth Partnership Team. And the mission of this team is exactly actually to support the partnership in mobilizing those resources for capacity building and skill transfer, and really embody this coordinated and complementary strategy. So now maybe just to finish, I mean, in this last part, just a few examples on what that looks like when we speak about a specific project. Typically in South Sudan, there is a team that contacted us telling us, look, the national government is interested in having better data and information on flood trends, hazards, and nature-based solutions to improve the resilient flood, the management of floods in the country, right? And so what we've been doing is that we've mobilized a team, and more specifically, I think the company that was working here was GMV, company from Spain, to develop products monitoring basically the trend in floods from 2015 to 2022 in order to inform the plans and kind of the public policies related to resilient flood management in the country. Once we delivered those products, then the World Bank aligned financing to develop capacity and kind of build more information and build skills in the country to use this information in order to ensure that whatever was produced was then transferred, and that this would really have a longer term impact on the way they work and on how they can use this data. Not always we can pretend that they will produce the data from scratch, but at least that they are aware of what can be done, and that then they better plan for the use of this data internally and throughout the different projects and the different development finance that they receive. So that's one example. Another example is in Pakistan. Here, it was more about agriculture drought and sedimentation assessment to improve water resources management. Again, here the complementarity has been with the World Bank actually covering the development and transfer of a decision support system to improve the resilience of irrigation and flood protection infrastructure. So again, here it's not even anymore about building skills, but it's actually about building a system that then can be integrated by the local stakeholders in order to continue working with this type of data. Yet another example is digital MRV systems. Here, basically what we've done is that we've mobilized a team in Mozambique to develop an Earth observation model to assess forest biomass. And this fed actually in the implementation of an MRV system for land use related GHG emission reduction programs to increase the efficiency of result-based carbon finance transactions. So this specific example is on Mozambique, but it has actually the potential to be scaled up at global level. It's just that, of course, those topics are very complicated and we're still in the piloting phase. Depends a lot on the availability of in-situ data. But let's say that there is this perspective of potentially scaling this up. And one final example actually is an example on Kinshasa on natural-based solutions through which we supported the design and suitability analysis of natural-based solutions using green infrastructure mapping. So here, what was interesting is that in addition to doing capacity building or transferring a system, the World Bank covered basically the implementation of a citizen science and micro-tasking based approach to ensure accuracy of analysis and foster skills transfer. So in short, on this example, in addition to having those more traditional approaches to building a system and building capacity, what was specifically interesting, and I think that's where really the value of those partnerships lie, is that we built on the expertise of the World Bank on citizen science approaches, microtasking, local participation of stakeholders, and really building those tools and the way they're implemented with the local communities. And that's I would say where the whole impact of those approaches lie, which is that we have the technological expertise at ESA, at World Bank, or the other international development banks. They have the expertise on building capacity, organizational change, citizen science sometimes. And if we combine both, we can really achieve a much higher impact on through the longer term adoption of those technologies throughout the world. So that's basically what I wanted to mention today. I'm checking two other slides. This last one is exactly what I was mentioning here. That's basically the strategy and the blended approach of the Digital Earth Partnership, which is, as I was mentioning, the counterpart program that was created within World Bank to accompany this change and implement this partnership on the side of the World Bank. Here you can see that the pillars are local participation, Earth observation, and artificial intelligence. And if we manage to combine those three and build a scalable model, we can really have a large impact across the whole portfolio and across the world as it stands, considering the scale of the World Bank portfolio. So that was quite dense, but I wanted to make sure I could make this in a short time frame. So let me know if you have any questions. Happy to answer.
Thank you so much. This is extremely interesting. It's great to see the impact of a program like ESA's GDA on mainstreaming Earth observation. And I do have a question, but I do encourage participants to please type your questions on the Q&A box. But I do have a question. In some of these countries where the program is active, there are some significant deficits, for instance, in terms of training or skills available. How is that addressed, or is it addressed? And what's the role, for instance, of local companies? Do they uptake the solutions? Is there a technology transfer, knowledge transfer? How does that work to ensure long-term sustainability?
Yeah, indeed. Yeah. So I mean, something that we're working and thinking very hard about is how to ensure the emergence of an ecosystem in some of those countries, right? So when I was discussing about capacity building and skills transfer, you have different ways to do it depending on the type of stakeholders you have how strong their baseline skills are. In some countries, we can afford to just train 30 people in a unit because it's a very niche application we're pushing, and it will be useful for us. But let's say that would be the traditional way to do things, right? What we're trying to push more and more are approaches based on liaising basically with local universities to encourage the integration of Earth observation or GIS into curricula, and then not only do this, but then link those to potentially even incubation programs in order to encourage the creation of potential companies, and then really create an ecosystem within those countries that will drive innovation, so that local ministries and local public institutions can work together with this private sector, right? The issue is that this takes a much longer time, right? So we need to somehow combine both and see what works in which countries, depending on how the economy is and the baseline skills are. But we are trying more and more to combine those things, and this is exactly the part that is covered by the World Bank in this kind of partnership, right? Where we do the technological development, but having the two integrated the best as possible allows really to have the highest impact, because typically one of the developments I was showing, which is the one on Kinshasa, deals on the fact that we are training people on the ground to use Earth observation, because then they do the microtasking, which feeds back the algorithm or the machine learning pipeline that we have, and then they through this process we improve the output of the analysis that is being done by European companies, and at the same time we upskill people on the ground, which they get more awareness about how this works, and then they continue potentially working on those specific topics and in the sector of Earth observation or geospatial data.
Thank you so much. I would open the mic to the previous speakers who are still online. If you want to ask questions or if you want to make comments, please do so. It would be nice to have some discussion now. I'm looking at the Q&A, so no questions for now. So waiting 1 minute. But this was really okay. We have Sudhir showing the camera. Sudhir, want to say something?
No, actually, thanks, Vasco. It was a really good talk. I just wanted to say thanks to everyone for taking time actually to join us as well. But I also wanted to hear if there, I know people may or may not be exposed to some of the forecast model data sets that we provide as a part of NOAA. And if there is of any interest, I'd love to have please reach out to us as well. And they can reach out to you as well to help us. But definitely this is something we would like to extend more, because what I talked about a lot more on the little bit on the data pipeline side, not the front end, right? Because but I think this sort of converges into maybe next discussion around, like, how we build the pipeline to front end development as well, right? So that will be good discussion, but I'll be interested to hear if they have anything on data optimization they were interested to hear about, or if they have any feedback, happy to take that.
Yes, thank you so much. And we'll be collecting questions. We have been receiving a few questions via email. We'll be collecting those questions, and also through the working group we're launching. And we'll redirect those questions to the speakers who address those topics. But by the way, Alex, I'll take the chance you're here. And so the cloud is also, I mean, the future for Earth observation. How is that reality in, for instance, the countries where the GTA is active with projects? And I saw some examples in Africa, for instance, where connectivity sometimes is challenging. How are you taking that into account?
The issue of connectivity?
Yes, to deploy cloud-based solutions.
Yeah, no, indeed, it's a huge issue. And we essentially, this is also something where we try to work as close as possible with other departments of those same large institutions, international financial institutions that focus on infrastructure, right? On the connectivity, on submarine cables, and so on. in order for, because of course you won't be able to use Earth observation if you don't have connectivity, even less if you don't have electricity. So all this, I guess, are kind of a package that we need to move on together. And I think that ends up being the bottom line, which is that, and that's what I was mentioning regarding accessibility and availability of this data. If you want the uptake and really the adoption of those technologies to happen, you cannot only work on one dimension, you need to work on all of them, and you need to coordinate along all of them. And the best you can do is to ensure that if you have several actors that are pushing, increasing connectivity in a place, then you can align a pipeline of activities instead of being scattered and someone working there, the other person working there. If we manage to really coordinate on this agenda by providing some institution providing connectivity, ESA and other international space agencies working on promoting the use of technologies and then building capacity on the ground, that's how we will achieve the goal, right? So maybe one last thing on this, which I think is important, is that the reality is that for us to coordinate, we often assume that coordination will happen if we have good intentions, but the reality is that coordination needs time and resources. And we often do not allocate enough time and resources to this because, of course, we have so much on our plates, all of us anyway. But we often underestimate the amount of time and resources that coordinating well takes, right? And this is something that happens across the board. And I guess if the more we think about how to make this coordination more efficient and how to allocate a reasonable amount of resources and time to this, the better it will go for all of us.
Thank you so much. This was really interesting. And this concludes session 4 of this workshop. Thank you so much to all the speakers. It was a real pleasure to have you all sharing your insights, your research, your work.